Course 3, Lesson 59, we are doing experimental probability. Now, experimental probability, rather than theoretical probability, we are looking at what actually happened. Theoretically, that's what we imagine is going to happen. But once we do experimental probability, we've done experiments, so we know what has happened. And our ratio, our fraction, is the number of successes over the total number of experiments. So let's give some examples of this. A softball player has hit 21 out of 60 at-bats. Express the probability that she will get a hit at her next at-bat as a decimal number. Now, with experimental probability, we're going to talk about how those 60 at-bats is the total number of experiments. So we have it over 60. And the 21 hits are the successful ones, which means we can reduce this to 7 out of 20, which as a decimal is 0.35, or as a percent is 35%. Meaning at her next at bat, she could get a hit 35% of the time. Now, what if we wanted to know that the probability of not getting a hit? Well, then we would be talking about, we still have 60 at bats, but instead of 21, we have 39 that she did not hit, which means that as a reduced fraction should be 13 over 20, which as a decimal is 0.65 or 65%. She has a 65% chance of not getting a hit. These are what we call complements because we have an event and not the event. They complement each other because they always add up to one whole, okay? Let's try another one. A salesperson distributed free samples at the mall. 50 shoppers accepted the samples and 30 did not. What's the probability that a shopper at the mall will accept the salesperson's samples? Well, the total number of experiments is the total number of people that they saw, which in this case is 80. And the ones that did accept the samples is 50, so 5/8, or 0.625, which as a percentage is 62.5%. Now, if we want to talk about the ones that did not accept the sample, that's the complement, which in this case would be 3/8. Because it always adds up to 1. So we have 0.375 or 37.5%. Okay? Those are complements of each other. Now, let's think about this example. The commuter plane flight arrives on schedule 2/3 of the time. Okay? Heather wonders what the probability is that it will arrive on schedule on a Tuesday, Wednesday, and Thursday in the same week. Is it practical to use experimental probability on this problem? What we're really looking for is what experiment would we have to set up in order to figure this out? And we would have to say, well, in order to get enough data, she would have to look at the plane schedules and figure out if the planes came in on time each week on a Tuesday, Wednesday, and Thursday for multiple weeks in order to get a good experimental probability, which is not very practical because that would take a lot of time. And that 2/3 of the time that we have earlier in the problem, that's more of like a theoretical. It typically comes in 2/3 of the time. So experimental probability would be pretty hard to keep track of in this case. Possible, but pretty hard to keep track of. And then another one. This is really looking at some strategy in a basketball game. So when a member of the opposing team fouls a basketball player who's shooting, the player shoots 2 free throws. Near the end of the game, a player has made 6 out of 20 free throws. So his experimental probability for free throws is 6 out of 20, or 30%. Whereas his percentage for 2-point shots is 60%. So when the player has the ball in 2-point range, should the opposing team foul him or risk the shot? Because they want to probably stop the time so that they get a chance to shoot the ball. So they want to know, should we defend him or foul him for this? And we would say we would probably foul him because his percentage of getting free throws is a lot lower than his 2-point shooting. So we would say let's foul him. because we could then get the ball back and shoot on our own end. All right, and another example. Quinn runs a shop. Since she added turkey melt to the menu, 36 out of 120 customers have ordered the sandwich. What is the probability the next person will order? Well, this is our experimental probability, 36 out of 120, which we can reduce to 3 out of 10. So 30% of the people are ordering this turkey melt. If she has 200 customers, how many should she sell? In essence, we would say, well, if we are getting 30% of people to buy this sandwich, if we have 200 people, we would say 200 of, or 30% of those 200 people we would get is 60 people. We would assume that she would sell about 60 of these sandwiches to 200 people. So she needs enough supplies for all of that. Well, I hope this is helpful for your homework and for studying.